Okay, so last day we ended our discussion over here that why we will non choose for non-determinism, and we have seen that there are some problems that is easier to solve or easier to realize the solution if we have an exhaustive search or a process of backtracking, and that means that from a particular state of mind you may go to more than one state of mind for checking for some same type of input, so that is which is not possible in deterministic finite automata, because DFA suggests that for a particular input from a particular state you can go any one other, any one state among the others. But again the question arises that whether non-deterministic finite automata is more powerful than deterministic finite automata or not, and our answer was no. So why we can do the, how we can say this? Obviously we have to prove it. So we will start with this proof first. So we will see the equivalence of DFA and NFA. But naturally there are some question arises regarding this equivalence. Question number one, is there any language L that is accepted by a DFA but not an NFA? And in an opposite way, the question can be, is there any language L that is accepted by NFA but not by the DFA? So if there is at least one language L that I can find for the question number 1 or question number 2, then I can say that yes, somehow DFA and NFA are not equivalent. But let's see. There are some observations we have already seen in previous lecture that every DFA is an NFA. Why I am saying this one? The reason is that if I consider a situation something like you are in a state Q0 and there are many more states over here, and the DFA suggests that from this particular state you can go to this state if your input is say some A. For the same input you cannot go from any to any other state. That is fine. And what this NFA suggests? NFA suggests that from this particular state, for the same input A, you can go to this particular state, or maybe you can go to this particular state, or maybe you can go to this state. So you have some option. So among these three options, jumping from this state to this state is also an option. So that means this, if I forget about these two states for time being, if I consider that I have only this state and this state, and I have a direction towards this for this A, I can say that this is a DFA as well as this is also an NFA, because jumping from this state to this state is also one of the options. But yes, we can say that DFA is only a restricted NFA. Restricted in the sense? Restricted in the sense that you have only one option. In case of NFA in a broader sense, you have n number of options. But in case of DFA, you have only one option among those n. So we can say that this DFA is a restricted NFA, but it's also an NFA. So naturally, if I can say that if L is a regular language, why we are saying regular? We are this regular language is coming into the picture because DFA, NFA, all these finite state machines basically accept the language which is regular, which is generated by some regular grammar. So that's why this regular language term coming in the picture. Anyway, so what it is saying that if L is a regular language, then there exists an NFA such that L equal to LM. What does it mean? Mean that there must exist some NFA machine, the machine we are representing by capital N, that accept the language which is basically the language generated by the machine. They are same. Now, obviously, it follows that NFA accept all regular language, but naturally question will arise, is there any more cases that, is there any other cases which is accepted by an NFA, even which is not regular? So if there is more language, beyond the regular language, which is also accepted by a NFA, then I can say that yes, DFA, NFA is much bigger set from the language or machine point of view than DFA. But let's see. So let's start with this example that we consider this. This is a DFA, right? Why it is DFA? Because you see, whatever states you choose, Q0, Q1 or Q2 doesn't matter. For a particular input, say A or B or C, you have only one option to go from Q0 or maybe Q1 or maybe Q2. For example, from Q0 for A, you can only go back to Q0. For B, you can only go back to Q0. There is no options to, there is, there is no two option for the same input A or B. Okay. Even if you get C, then you can go from Q0 to Q1, and same thing for Q1. So what basic thing we can find over here, that to reach to final state Q2, since this Q0 is the initial state, to reach to this final state, you have to have at least 2C or maybe more, but at least 2. So I can say that this particular machine or DFA can accept any combination of A, B, C, but having at least 2C, right? And the corresponding delta function, the delta function table, actually this is actually what we call transition table, right? So the transition table look like this, and you see we have in the left side, this is the states and these are the inputs. So if you are in state Q0 and if you get A, you will remain in Q0, and that is the only option. Now if I want to do the same thing with the NFA, obviously the machine will not change, the architecture of the machine will not change, but from the NFA point of view, you know that the transition function for a NFA we have already seen is something like delta is what? Delta is basically a state with the alphabet which maps to 2 to the power q states. Why 2 to the power q? Because we have all the options. So that means, from, if I consider that say there are two states A and B, what we can do? We can say that the delta of, say you are in A and you got 0, you will remain in A. It is possible. You are in state A, you got 1, sorry, you got 0, for the same input, obviously, right? So the input will not change. So if you get 0, maybe you can go to B. There is an option. It's possible. For the same input, you can go to two different state for an NFA. Even there is an option. You can go from state A. Because of this 0, maybe there is no option what to do, what to go. It's not defined. If it is not defined, that means you are going to find some empty state. So what are the possibilities we can see over here? We can say that we have a possibility to go only state a set which contain only the state a set which contains only the state B, a set which contain this phi, and a set which contain both possibility A and B. But there is no more options over here, because these are the four possible cases, four possible subsets of this particular state A and B. If I consider this is a machine, some NFA, and there is only two state A and B, so the four possible subsets can be something like this. So here Q is equal to 2, and this total number of subset is basically equal to 4, right? Total, which is basically 2 to the power Q. So we can easily prove this with an example. So that means if I want to do the same thing, if I want to accept the same language with an NFA, since the machine will not change, what will change? The writing style of the transition function will change. You see, if you take a difference between, if you want to notice the difference between the state diagram or the machine, you see they are same. The difference, even the Q, sigma, the starting state, the final state, nothing is changing. Only the state changing is the way of representing the transition table. Instead of only writing Q0, we are considering this Q0 is the only state in this set. Why set is coming? Because there is a possibility to go more than one state at a time. So we have to find what are the subsets possible from where the machine can go from a particular state. And since in this particular state diagram there is no cases where we have a possibility to go more than one state for the same input from a particular state, and that's why in every subset you will find only one state, not more than one, not even 5. So with respect to this situation, I can say that this is an NFA, but a special type of a restricted NFA where you have only one option to go to one of the states from a particular state for a particular input. And this is a true DFA. But you see, if you don't confused with this two situation, what I mean to say is that NFA does not guarantee that you must have two options every time, at least two options every time to go to two different states from a particular state. It may happen you don't have any option, but that does not mean that is not an NFA. So the equivalent NFA should obviously look something like this, where nothing will change. Now, if we must prove it by some lemma, what we call, or some theoretical background, some proof. So let's go to this. There are two lemmas. So let's go to the lemma one by one. What the lemma one is saying, that let M be an DFA. So M is a machine representing a DFA machine, and M dash is representing a NFA machine. Suppose, and it is saying that let M be a DFA, then there exists a NFA M dash such that this LM means language accepted by M. LM dash means language accepted by M dash. What it is saying, that there exists a NFA M dash such that LM equal to L of M dash. Mean the language accepted by the DFA and the language accepted by the NFA will be same. How we can prove it? We can just take a formal statement or observation from the previous slide to realize this particular lemma. We have already seen that every DFA is basically NFA. So if every DFA is a NFA, that means we can, if we let that M dash is basically equal to M, just we have seen from the previous example, then we can easily say it follows L of M dash will be L of M. Now let's go for the lemma 2. So lemma 2 is saying just an opposite situation. It's actually arising just opposite situation. That it is saying that let M be a NFA, then there exists a DFA M dash such that L of M equal to L of M dash. The same thing, but we are claiming that there must exist a DFA for a particular NFA. So let's try to realize this lemma with proof. What it is saying, that suppose we have a situation something like this. So suppose we have a machine M. So this particular machine M is representing for a NFA, right? And this symbols you already habituated. So I don't need to. I hope you don't need. I don't need to explain these symbols. Now we have a definition of DFA, a definition of DFA over here. Since obviously we are initially imagining, we initially considered that this machine and this machine are different. That's why you have taken it M dash, where the symbols are just different. But remember, the sigma remains same, because ultimately we want to work with on the same symbol, and we have to verify whether this language is same or not, that is accepted by the machine M and M dash. Now in this particular DFA, the Q dash that we have, you see how we can define this Q dash with respect to this NFA. We can say that Q dash equal to 2 to the power Q, as we have seen, because this each state in M dash corresponds to a subset of states from M. What does it mean? It means that if I consider in an NFA, for example, there are 3 states possible. Okay, 3 states. So maybe A is a state, B is another state, C is another state, AB is another state, A comma B, B comma C is another state, C comma E is another state, A, B, C as a whole can be another state possible, and obviously phi is also possible. You see, total number of subset of the states are 8. 2 to the power Q equal to 8. So that means you can say that from A, in an NFA, you can go to, say for symbol 0, you can go to A, you can go to B, you can go to any of these 2 to the power q states for the same symbol 0, suppose. So what we are doing in this DFA, we are representing q dash, we are actually representing these states A, B, C, A, B, B, C as individual states in the DFA. So that means just try to assume a situation that we are trying to map these states, say, sorry, okay, say this one is q0, in my DFA q1 is this, in my DFA another, in the equivalent DFA actually this is q2, this is q3, this is q4, and maybe this is maybe q8, so on. And that's why I have written this 2 to the power q. So this q0, q1 in this way, say q8 is the total 8 possible states in my DFA possible. And where this q u equal to this, and what this is representing, this is representing actually some combination of the actual states, that is A, B, C, some combination, actual state name. And we can represent this f dash, that is the final state, as qu, such that this qu contain at least one state in f. What I mean? It means that in the NFA, if we assume that this C is the final state in the NFA, that means I will take q2 as final state, I will take say q4 as final state, I will take say q4, q5, q6, q7, it will be q7, it should be, and q6. So I will take q5, q6, all these 4 as a part of the final states, because all contain C. And naturally this q0 will be this one, and this q0 can be some state, single state, or a subset of state, whatever, it depends upon the situation. And we can write the transition function delta dash in this way. Just assume that qu is some state and qv is some another state. I can write the delta dash of this DFA with qu as input state, with initial some state, and if this A is the input, you can go to qv. This particular transition function can be written if and only if there is really a path from qu to qv for this A. Then only I can put it. And in this way I can design this in dash. So after designing this, naturally this particular set of states, for example, maybe some you can ask me that still why this DFA will accept the same language. So just let's take a very simple situation. As we have seen that C is basically the final state, it was in the NFA. So that means there is a state C, and from some another states, if it come with some input, say 0 or 1, since this is the final state, obviously the machine will accept the string. Now from where this 0 is coming? Is there any What are the possibilities? The possibilities can be, it may come from A, or the situation can be it may come from B, or the possibility is that it may come from, I mean, take another situation, from A to C. At the same time, it may come from B also. So these are to another state, right? For the same input 0. Even it may come from A, B, C as well as, I mean, A, B as well as C. So that means we have a possibility number 1, possibility number 2, possibility number 3. Actually, possibility number 4 I have written over here. So let's write it individually. And possibility number 4 is something like a situation like A to C for some input 0, even from B to C, even from C to C itself for the same input. And this is possibility number 4. So this is what actually this transition function is saying. Since, for example, let's take, we are taking this say Q3. Okay. Not Q3. Okay. I mean, okay. Let's explain in a different way. So what I mean to say actually that we have these 4 possibilities. If any one of them is used to reach to C, then I can say, I mean, I can write in DFA that maybe, for example, say for example CA, this Q5 is a final state in my DFA. I can do a cycle, I mean self loop actually within Q5 for some input say 0. If I find that there are a possibility, oh, there are a possibility that from C it is going to C, even from A it is going to C. Forget about B right now because we are considering Q5 which is representing CA. So in the NFA, if I find that from C there is a self loop for 0 to C, and from A there is a path to C for 0, that means as a whole I can write this for in, I mean this too, I mean forget about this B right now. If I just forget about this B part right now, this particular situation, this particular uh, situation we can show in this way, because this Q5 is representing the state C and A as a whole. So with Q5 we will have a 0, and this is what actually explained over here. And if it is possible, that means what? That means obviously this particular DFA will accept the same language, actually will accept the same set of strings which is accepted by the NFA. So that means, in other words, the DFA is accepting the same language accepted by the NFA also. So this lemma 1 and lemma 2 both as a whole can easily prove that there is no difference between accepting the set of language by a DFA and some NFA, corresponding NFA and the DFA. So in this way we can actually realize the equivalence of DFA and NFA in automata theory.